In this video, we'll learn how to find the A basis for a null space. Really, we already know how to find a basis for a null space, because to find a null space, if you've got a matrix A, to find the null space of A, you solve AX equals 0, which hopefully you are by now capable of doing. You just do a little Gauss-Jordan elimination. Theorem. When we solve AX equals 0 and write the solution parametrically, the vectors that appear are a basis of the null space. Let's see how this works with an example. In particular, this example. So to find the null space, we need to solve AX equals 0. To do this, we take the matrix A, we augment it with the 0 vector. Then we perform Gauss-Jordan elimination. The variables x sub 1 and x sub 3 are basic. The other variables are free. The first row gives us an equation for x sub 1. The second row gives us an equation for x sub 5, x sub 3. The third row rather unhelpfully tells us that 0 equals 0. I'm going to pause this recording now, and what you'll see when I unpause it is an equation for x sub 1 with x sub 1 by itself on the left, We'll move all of these over here. And an equation for x sub 3 with these two terms moved over on the right. We are now going to add equations for the free variables. But the free variables are free. What could we possibly say about them? Well, we could say that they are equal to themselves. And now, and I know I'm going a little fast, but this is a process we've seen before. I'm going to fill in any missing terms with zeros. And what we then read off is that the vector x1, x2, x3, x4, x5. This is a vector in the null space, is some free variable times the vector 2, 1, 0, 0, 0, plus some free variable times the vector 1, 0, negative 2, 1, 0, plus a free variable times negative 3, 0, 2, 0, 1. So any vector in the null space is a linear combination of these three columns. So certainly these three columns span the null space. In fact, they're a basis of the null space. They are linearly independent. How do I know that? Well, notice that the vector associated with x sub 2 has a 1 in the second coordinate. The vector associated with x sub 4 has a 1 in the fourth coordinate. And the vector associated with x sub 5 has a 1 in the fifth coordinate. And the other second coordinate's 0. In the other fourth coordinate's 0. In the other fifth coordinate's 0. If this set were dependent, at least one of these vectors would be a linear combination of the other two. Any linear combination of these two vectors has a 0 in the second coordinate. So this isn't a linear combination of the others. any linear combination of these two vectors has a 0 in the fourth coordinate. So that's not a linear combination of the others. And I have already forgotten which I started with. This third vector isn't a linear combination of these two vectors because of this 0 and this 0. Any linear combination of these has a 0 in this coordinate. I think that was the one I hadn't already done. And this is true in general. That is to say, for any matrix A, once you go through this process and you get the vectors in the null space written parametrically, the vectors you see will be a basis of the null space. In this video, we learned how to find a basis of a null space. As part of that, we reviewed writing solutions of matrix equations parametrically, an important skill that people did seem to struggle with on the first test.